All right. So thank you very much for inviting me to speak with you today. I thought I would try and introduce myself because I've never visited your institution. And so I've worked on teams that have used radio telescopes to try and find evidence of someone else's technology. I'm the one that isn't wearing the headphones. I have degrees, as you just heard, from Cornell in engineering physics and a PhD in astrophysics from Berkeley. I was the project scientist for NASA's SETI project. I was the first employee when we co-founded the SETI Institute in 1984. And I've never had any job except working on SETI. So a number of projects that we've done. And I also served as the president for the California Academy of Sciences for a couple of years. And I had just received an honorary doctorate from the University of Pennsylvania. So I am formally retired, but I am still cheerleading this SETI activity because I think it's the most important question in the world. Are we alone? So some of you may be familiar with biosignatures. This is an activity under astrobiology's umbrella to look for disequilibrium chemistry in the atmospheres of distant exoplanets. So in particular, one of the things that characterizes the atmosphere of the Earth and doesn't appear in the atmospheres of any of the other planets in our solar system is the coexistence of oxygen and methane. Those are very reactive gases. They are always combining in the atmosphere to produce carbon dioxide and water. But because we have such a strong biological source function on our planet with photosynthesis and bovine flatulence, cow fart, putting these gases back into the atmosphere, we find them coexisting in a non-equilibrium condition. And if and when we develop the telescopes and the spectroscopic tools to do this kind of observation of another planetary atmosphere outside our solar system, these are kinds of things that we're going to be looking for as an indication of biology on the surface. Now, you're probably aware of a controversial claim of the detection of phosphine in the Venusian clouds a few weeks ago. And there are a couple of questions. One, is the line identification correct? Is that really phosphine? And two, how is it produced? Because looking at all of the chemical pathways and networks that the authors could think of, they could not manage to produce this amount of phosphine. And so on Earth, we find phosphine in areas where there is no free oxygen, and it is produced with life as a fundamental part of the process. So this is very, very intriguing. Have we perhaps found evidence of life in the Venusian clouds? And quite controversial. So the jury is still out on this one. But what we are looking for at the SETI Institute and the Berkeley SETI breakthrough teams are looking for is not biosignatures, but technosignatures, looking for something that has modified its environment in ways that we can sense with telescopes remotely that we don't think can be produced naturally. So technosignatures and biosignatures both fit neatly under the umbrella of the discipline of astrobiology. And we're trying to find habitable worlds through the actions of the inhabitants. So what we have been doing for 60 years now is to search for some kind of communication. It started in the radio with the first search in 1960. Then at the turn of the century, we began looking for signals with optical telescopes. And so we're looking for a signal that is obviously engineered, not something that Mother Nature can produce. And two of the telltale signs of engineering would be compression, either in frequency, so a very narrow signal occupying only one channel on the radio dial, or very, very short pulses lasting a nanosecond or a microsecond. Again, we don't think that nature can do that, but we can do it in our laboratories. So we're looking for a single frequency on the radio dial or single nanosecond pulses in time. And then we're also looking for monochromatic laser signals. That is, again, not one frequency on the radio dial, but one frequency on the optical dial. So a laser that is at a particular frequency, and that might be being used, for example, to accelerate starships, as the Breakthrough Starshot project is looking into from our own technology. So there are signals that are not only obviously engineered, but there are signals that are almost natural. And for some reason, I've lost the audio on this, but this is a diagram of a pulsar. All right, it's like a lighthouse beacon, and when it passes across the Earth, we hear a burst of radio frequency emission. So what if we went looking for pulsars and found a pulsar that had a particular period, and then the pulsar changed its period? Now, this happens because of starquakes in the neutron star. But we've never found a pulsar that has started at period 1, changed its period to something else, but then went back to its original period. But if we found something like that, that would be interesting. Another type of signal that would be interesting as a technological marker might be artificial transients. We have been finding extrasolar planets by looking at them passing in front of their star and casting a shadow. The IAU tells us that planets have to be spherical, so that shadow will be round. But perhaps another technology has the ability to launch some very large-scale structures to artificially orbit their star, and their shadow will not be round. So as you begin a transit and as you exit a transit, ingress and egress, if we look at the high order moments of that light curve, we might in fact be able to discover a non-round shadow, and that would be interesting. Okay. Here's another idea. Suppose that you have the ability to build a large neutrino factory and put it in orbit. And you put it in orbit not around the sun, but around a Cepheid variable star. This is a star that naturally expands, gets brighter, then collapses again to its original size, and then does it again. And the periods of these are very fixed. But suppose with your neutrino factory orbiting around a Cepheid variable, you wait until the star has collapsed and it's getting ready to expand again, but you zap it with an energy source or a neutrino beam and you make it expand prematurely. Well, then what you've done is you've created a giant interstellar Morse code with a regular period, a long period, and a short period that's indicated by your instrumentation. And so you could, in fact, have beacons that can be seen all across the galaxy. They can actually be seen to the Virgo cluster of galaxies. that have this Morse code that could be modulated. And that would be almost natural too. You might, in fact, if you want to communicate, might decide that you don't want to use the electromagnetic spectrum. Instead, you want to take small meteorites and inscribe information interior to those meteorites at atomic scale. You could have a very high density of information. And then you essentially just launch these rocks between stars, between planetary systems. Now, that's a very slow way of communicating, but it is a way of getting a great deal of information transmitted, potentially. So we've been thinking about this for 50 years. And the question is, how much of the search space have we actually investigated in that 50 years? And the best thing I can do to try and make a point here is, and I did this when SETI turned 50, was to say that we have a multi-dimensional search volume to look at. We have all the places on the sky, we have all frequencies, we have polarization, and we have information, content, and modulation, 9 dimensions altogether. And if I make an estimate of how big that volume is that we might have to search to find a signal, then it turns out that if the search volume is set equal to the volume of all the Earth's oceans, that in 50 years we'd searched 1 glass of water out of that ocean. And then 10 years on, it's more like a small hot tub's worth. So our searches are getting better and faster, but there's a lot left to look for. So what about other ways to send information? We've been talking about electromagnetic waves and rocks, but if we send any kind of matter, you want that matter to be neutral, because you don't want the magnetic field lines in the Milky Way galaxy to take your message and turn it off course. You probably want them to be massless because that requires less energy. Possibly entangled pairs could be created and separated, pairs of particles, pairs of photons. Possibly you might be able to modulate gravitational waves if you have large enough masses. And there's always the wonderful science fiction faster than light travel via wormholes or warp drives, right? So there's a lot of possibilities. And here's a table that was made by Michael Hickey about what the degree of difficulty might be in exploring any of these types of information carriers, right? And you can see that the degree of difficulty is very high for some of these extreme ideas. So for now, given the technology that we have on this planet, we're going to be continuing to search for electromagnetic waves, for photons. But what about searching for artifacts? I think that's feasible only within our solar system. Looking at the Earth, Moon, Mars, asteroids, Lagrange points, Venus now, perhaps. And on Earth, as we look at the history of our civilization, we can go back maybe a few thousand years. Archaeology takes us back perhaps 10,000 years, and things that are written into the geology of the planet can maintain and last for perhaps 100 million years. So there's a lot of search possibility there. It's even been suggested that a neutrino beam could modulate the decay rate of manganese 54 that radioisotope, and that we might see the decay rate of this isotope changing in our laboratory in a way that might suggest information content. All right, how about the moon? Well, what about the monolith, right, from the 2001 movie? We have so far imaged the surface of the moon, but we haven't explored the subsurface. So anything that was subsurface or less than about 10 meters in scale, we would not have discovered. And so the GRAIL mission of orbiting 2 satellites around the moon discovered some mass concentrations. And so possibly that could be showing us something that is buried beneath the surface of the moon. It might eventually turn out to be an artifact or technosignature. The Lagrange points, right, are special points in here, the Earth-Moon system, where gravity is fairly well balanced. And if you wanted something to remain in orbit for a long time, these Lagrange points might be something to develop. And sometimes when people have looked at the Lagrange points, some have claimed that they see what are called Kardalushki clouds of something. Not sure what it is, but it's been suggested that if those clouds are real, they perhaps could be tiny little nanobot artifacts of someone else's technology sent to our solar system to attract our attention. Likewise, we could look in the asteroid belt, looking for artificial lighting on an asteroid as a potential technosignature. And although I thought that searching for artifacts was only going to be feasible within our own solar system, then we had this incredible piece of something called Oumuamua enter our solar system from interstellar space, from having originated in another solar system. So in fact, perhaps there is an opportunity to look for artifacts sent into our own solar system. And everyone who has ever read Arthur Clarke's Rendezvous with Rama thought about that as we had a fleeting few weeks to observe Oumuamua as it we found it as it was already leaving our solar system. But there will be others. So indeed, perhaps we can look for artifacts from other solar systems as well. So it's been suggested that when we get the ability to image distant exoplanets, which we can't do very well at all right now, that we might find the evidence of dead worlds, of civilizations, technological excess that in fact led to the demise of those distant planets. And so the technologists would not be there, or the biologists would not be there now, but there might be some presence or evidence that there once was such a presence. So we can ask another question. What do technologies do, and what might that tell us about what we should be looking for? Well, they harvest energy to do work, and with different levels of efficiency. So depending on whether the energy is chemical or wind, solar, wave, geothermal, nuclear, or something else, they might have detectable outcomes. So the observable consequences for these different energy sources, it could be pollution of the atmosphere with this sort of industrial waste, CFCs, that we have been putting into our own atmosphere. And if you could get 2 days of observing time on the James Webb Space Telescope, if and when it ever launches. And assuming that this industrial pollution was happening at a rate that's 10 times what we're doing on Earth, then it would be detectable and an interesting signal, perhaps, of technology. If you're doing nuclear energy generation, then if you're doing fission, you have the problem of fissile waste. How are you going to get rid of that radioactive waste? And one suggestion was you could dump it into your star, right? And if you did that in sufficient quantities, then you would raise the abundance of some rare earth elements in the sun's spectrum, like neodymium and praseodymium. And indeed, we have seen one star that has this crewy abundance of these rare earths, and it's called Cybulski's star. There's probably a more mundane explanation for the Cybulski star than disposal of fissile waste, but it is an intriguing idea. And if it were fusion rather than fission, you might, because fusion is dirty, you might want to put it in orbit. And as you're running your nuclear fusion plant, there might be some leakage of tritium from that plant. And tritium has a radio line like the hyperfine 21 centimeter line of hydrogen, neutral hydrogen, except it's not at 1420 megahertz, the way the hydrogen line is. It's at 1516 megahertz. And so if you go looking for that line and find it anywhere out there, except in the vicinity of a very recent supernova, you're going to be very puzzled, because this tritium has such a short half-life. Half of it disappears every 12.6 years. So detecting tritium might also be an intriguing technosignature. Well, what kind of work do technologies do? They want to generate, store, and transfer information. They do some construction, transportation, large scale, resource extraction, manufacturing, and replication. They might want to maintain homeostasis. They might want to keep conditions on their planet just so. So if we transfer information, well, that was kind of the things that we were talking about earlier with respect to communication. But suppose that this is an advanced technology that has the ability to travel between the stars with photon rockets. Then every time you accelerate with a matter-antimatter annihilation, you'll get a burst of gamma rays. And so when gamma ray sources were first found back in the late 1980s, it was suggested that those gamma ray bursts could be the acceleration events of these photon rockets. And so people tried to connect the gamma ray bursts in space-time to see if it was, in fact, a continuous trajectory. That didn't work. We have other explanations for gamma ray bursts, but this is something we might see sometime. We also thought that if it wasn't really fast ships, but slow generational ships that were going between stars, then they might enter our solar system and indeed use the asteroid belt to replenish some of the consumables aboard their ship. And so we should look for asteroids that had a little orbiting satellite around them. And we found them. The first ones that we found were Ida and Dactyl. It turns out Dactyl's just a rock. It's not a spaceship. But again, this was an idea for a technosignature. And then, as I've already mentioned, for accelerating solar sails. you might be able to see the laser, the monochromatic laser that's being used as the accelerator. Faster than light travel, I just put this up because I wanted to try and be inclusive, but I have no idea how we would look for that. So how about the homeostasis? How about trying to manage your planet in a way that would have observable consequences? So you might, if your star is fading, you might want to orbit large mirrors to bring starlight to the backside of a planet. The surface temperature of the planet might be wrong, given what its albedo is and how far it is from its star. On a very long scale, you could maybe become aware that there was no longer any extreme weather on that planet. And with enough energy, it might be possible to modify your planet so that the temperature from the poles to the equator was uniform, and so that you don't have frozen poles and hot equatorial regions. You might have a homogeneous temperature on that planet. And what about if you originated on one planet and then went to a nearby planet in your solar system, your planetary system, and decided to modify that planet to be like your home world? Well, here's an example of what I'm talking about. So we have this system called TRAPPIST-1, 7 Earth-sized planets orbiting very close to a red dwarf star. And when you see this slide normally, you'll see an artist's conception of what those different planets look like. Now, nobody's ever seen them, so we don't know whether that's a good representation or not. But suppose when we get the ability with very large telescopes to image planetary systems such as TRAPPIST-1, what if we found they were all the same? They shouldn't be. Those planets are at different distances from their stars, so they should be at different temperatures. But what if someday we make an image and this is what we see? Well, then you're going to really be thinking about geoengineering in a big way. We have a geosynchronous belt around the Earth, and we put a lot of satellites in geosynchronous orbits. What about making that geosynchronous orbit so full of satellites that indeed that belt becomes visible? Not a ring around the planet, not a thin ring that's extended in radial distance, but a fixed radius that is extended vertically, so-called Clark geo or exobelt. Maybe we could detect their technology that way. And finally, if you're going to be harvesting light and energy from your central star by building some sort of a collector, some sort of a Dyson sphere, then you will be ultimately modifying the properties of that star in a way that doesn't look natural. So these were some ideas about the consequences, observational consequences of work. So to follow up on that astroengineering idea and megastructures, there would be an infrared excess around the visible star because the backside of whatever your collecting area is would be warm and it would glow in the infrared. Stars, which you found in catalogs a decade or a century ago, might disappear if they were completely surrounded by this kind of astroengineering megastructure. And the spectroscopic distances that you would calculate for this star would be greater than the distances that the Gaia spacecraft and parallax measurements give, because you would have enclosed the star and make it dimmer and therefore appear spectroscopically to be farther away. And again, this idea of orbiting giant mirrors, because your planet might be tidally locked to the star, keeping one face pointed at the star, just like the moon keeps the same face pointed at the Earth all the time. And these mirrors could, in fact, then bring light to the dark side of the planet. And indeed, if you are mining resources in an asteroid belt, then perhaps that extraction process would leave a footprint that could be detected with large telescopes of the future. And suppose your society is no longer biological. Suppose that you have evolved to be very intelligent machines. Then what might the observable consequences of that be? Well, a machine, if given a goal, for example, manufacture 1 million paper clips, but the goal is not very tightly constrained, the machine is going to have to sit there and say, okay, have I made 1 million yet? Well, just to be on the safe side, let me make another 1 million, right? And so you might find that there's a certain uniformity that you wouldn't expect in nature for a super intelligent machine civilization living in the vicinity of a planet. So these generalized artificial intelligences, where might we find them? Well, it's been suggested that they require a lot of power. And so you would build what we call a matryoshka brain. Your fastest processors would be orbiting closest to your star. And then the next layer of slightly less capable processors will be run off the infrared heat coming from the inner layer, and so on and so on. And places where you can find sources of great energy are black holes, neutron stars, pulsars, and perhaps because all of this computing generates so much heat, and you have to be able to exhaust that heat against something that's colder, we might go looking for these at the edges of the Milky Way galaxy, where you don't even have the starlight to give you a slight warmth, but that would be cold at the edges of the galaxy. So a lot of different ideas that have been talked about over time, and new tools that will be coming online in the future that can allow us to try and look for these different kinds of things. I think right now, the biggest opportunities for doing things in a new way comes from trying to gain access to the transient sky. Most of the kinds of searches that have been done in the past have assumed that whatever is there is going to be there for a long time. But there are good models for observable consequences which might be short-lived. So you need to be able to see them and verify them very quickly. So neural networks and artificial intelligence being taken to build the back ends of new kinds of telescopes, I think are going to allow us for the first time to have confidence if we detect a transient signal. And it will also allow us to look for information in the output of telescopes that doesn't necessarily match a predetermined pattern that we told the machine to look for. but these neural networks can simply tell us about anomalies in data, about data that has information content in it, even though we don't know what the pattern that we should have been looking for is. So we've got lots of ideas for the future, and I'm excited that we are beginning to have graduate and undergraduate curricula on SETI and searching for technosignatures in various universities. So here's something that we did in Northern California called the Allen Telescope Array. It is an array made of a large number of small dishes. The main reflector in these telescopes is 6 meters across. We had hoped to build 350 of them, but we ran out of money and we had to stop at 42. But this is an indication of the kinds of things that we can do in the future. This is a way of building a very large telescope out of small pieces. And it's only possible now that computing has become fast enough and cheap enough. And so the Allen Telescope Array allows us to look for technosignatures, and it also allows us to do radio astronomy with high spatial resolution. Breakthrough Listen is the new game in town. It's been going for about 5 years, funded by Yuri Milner with a $100 million pledge for 10 years of observing. And they are now using telescopes. They're not building their own telescopes, as we did with the Allen Telescope Array at the SETI Institute in UC Berkeley, but they are using existing telescopes around the world with high-end, very fast computer backends. And so they are using an optical telescope at Lick. They've got equipment at the Green Bank Telescope in West Virginia, and Parkes in New South Wales, Australia. They're just starting to observe with Meerkat telescope in South Africa. They added some new software, though no new hardware, to the Veritas array of gamma ray Cherenkov radiation telescopes, looking with the 4 telescopes for the same pixel on the sky, single pixel to light up simultaneously. There's a very low frequency array in Western Australia, the Melora Wide Field Array, a brand new telescope in China that is 500 meters across, and a much more venerable large telescope at Jodrell Bank in the United Kingdom. And so Breakthrough Listen is bringing signal processing equipment to all of these telescopes to expand the search. SETI at Home has been going for years on the Arecibo telescope, which at the moment is out of commission because 2 cables that hold up the superstructure have broken. But when that is repaired, SETI at Home or something like it will be run again commensally, which means at the same time. So data that are taken for radio astronomy can be reprocessed looking for technosignatures. There's a low frequency array in Europe and England, and that's being looked at for low frequency transients. There's a small group in Italy that uses this this telescope at Medicina. High school students in Southern California are running a sky survey using an old 26-meter telescope that NASA provided. And here's the Melora Wide Field Array, which is growing into the future. Optical SETI was done for many years by this purpose-built telescope built by Harvard students looking across the sky for something like, it's 80% of the sky, and I think they've covered it a half a dozen times without finding an optical signal. The Keck telescope and an instrument called HiRes on the 2 10-meter Keck telescopes, that normally takes data looking for radial velocity information to find exoplanets. around nearby stars. But that same data can be repurposed and reanalyzed for laser signals, and that's been done. There's an optical SETI amateur observatory in Boquete in Panama. SETI is pushing into the near infrared from the optical with systems at Lick Observatory, and data that have been collected in the infrared by the WISE spacecraft over many years. Those data are being reanalyzed to look for the infrared radiation from Dyson spheres, or even a more advanced technology that can manipulate all of the power in its galaxy, all the stars in its galaxy, looking for infrared signals from that. So that's a data mining kind of search that we can now do. I talked about the gamma ray observatory for optical SETI. So those at the foci of those 4 dishes are essentially 1,000 small cameras, pixels. And what we're looking at for SETI is that just one of those pixels lights up in each of the cameras from the same pixel on the sky. Here's a new optical SETI backend that's being built, a telescope system that's being built. It's called PanoSETI. You can see in the upper left, Shelley Wright with a large Fresnel lens. And what Shelley is doing is building a geodesic dome with these lenses that focus light from a large area of the sky down onto very sensitive photodetectors that are now available. So if you built one of these, put in 126 Fresnel lenses, you'd be able to look at 10,000 square degrees on the sky at one time. And of course, you have to build 2 of them, because if you're looking for fast light pulses, you want to be sure that the transient that you found is a real signal and not just some instrumental problem. And so these 2 telescopes would co-observe the same 10,000 square degrees on the sky, and you'd require that you saw the signal in both. And here is one of the lens and back-end detectors that have been, actually 2 of them have now been installed at Lick Observatory, and they are undergoing engineering testing. And the rest of the construction for the moment is on hold because of the coronavirus. So there are the 2 engineering test models at the Lick Observatory. Another type of optical SETI observatory that will actually be able to look at all the sky all the time is called Laser SETI, and it's being built by Elliot Gillum at the SETI Institute. And each site has 4 cameras and looks from horizon to horizon, looking for bright optical flashes. And with something like 15 sites around the world, we can, in fact, get a system that is looking at the sky all the time, all sky. So here's the kind of readout that you get from the grading of that laser SETI instrument. And you can see the difference between a stellar source, which gives you a spread out spectrum, and a monochromatic pulse from a laser. And so you put the first 2 of these systems are on top of an observatory in Northern California, and you can see that the night sky looks a bit more daunting than the nice, clean picture I showed you here. But software has been written that, in fact, does interrogate all of those images looking for monochromatic pulses. There are two more of these systems that are waiting to go to Haleakala in Hawaii. Again, slow up because of the COVID problem, but that should be installed by the end of the year. And then, as I said, with multiple sites around the world, all the sky, all the time. Here's a telescope that's proposed, and it's the weirdest one I've ever seen. It's more like a radio interferometer than an optical telescope. Each of these mirrors is 6 meters across, and if indeed you could build this, there's only one system that it can really look at, and that's Proxima b. So the Alpha Centauri system, Alpha Centauri A and B and Proxima, are the closest stars to us. You could use this telescope to study Proxima b and measure its light curve through hundreds of orbits, and then you could deconvolve the light curve in a way that would allow you to decide whether there were continents or oceans on that Proxima b planet, and even do some biosignature work there. Again, this has been proposed. It's not funded. They're working on the technologies to make this happen. And that brings us to future telescopes and how we could use them for SETI, because we're not going to, with the resources of the SETI community, we are not going to build this next generation of 40-meter telescopes, but we should figure out how to use them commensally. So the 30-meter telescope, the Giant Magellan telescope, the European extremely large telescope, and then the large synoptic sky telescope, or the Roman telescope, for looking for transients. PanoSETI and LaserSETI will join these. Veritas is already working. The Meerkat array and FAST telescopes and the Square Kilometer array in the future for radio astronomy. We might, in this country, build the next generation of VLA telescopes across the western part of the United States. And if that funny ELF telescope, the Life Finder, can be made to work, then its much huger Colossus cousin could be used to actually, if you could build something this size, it would actually be able to see the heat signatures of any cities on nearby exoplanets. So a lot of potentially fantastic new technology coming up in the future. And in the optical, you've got the JWST, and then a Starshade, and 4 proposed new great observatories, Habex, Lynx, LUVOIR, and Origins, all of which are being proposed to the decadal survey being done in the US today, or in the next couple of years. We'll see whether any of those come out of the decadal with approval and funding, and we'll see how we might, in fact, try and use them for SETI. And lastly, the overwhelmingly large telescope that has been proposed for the backside of the moon. Who knows whether anything like this will ever get built. And then for searching for exoplanets, there's just NASA and ESA and JAXA and the Chinese Space Agency have lots of plans for searching for exoplanets. And some of them, by the time you get to LUVOIR or Habex, can in fact begin to look for life. So in summary, looking for life beyond the Earth, you can discover it in situ. You can find biomarkers, perhaps in our solar system. You can look for artifacts in our solar system. You can look for remote biosignatures in the atmospheres of exoplanets. You can detect the work product of technological civilizations, technosignatures, or perhaps you'll be able, when you build a telescope that will search the sky at some frequency for a certain type of astronomy, maybe serendipitously, those data will lead you to the discovery of some vast astroengineering projects. And finally, you can export it. we're talking about going back to the moon, to Mars, perhaps to the asteroid belt. And then we're talking about breakthrough starshot to send small, tiny 1-gram instrumentation packages to study the Proxima Centauri system. Now, I really thank you for listening to me today talk about this weird idea of technosignatures. And I really enjoy the opportunity to talk to people about SETI and technosignatures, because I think that the act of listening to the talk actually has the effect of holding up a mirror to all of us on the earth and saying, see, in that mirror, you're all the same when compared to something somewhere else that evolved independently. We're all earthlings. And I think that's a message that we have to internalize, because we have so many challenges facing us in the future: water security, food security, all kinds of difficult things that don't respect national boundaries. So, last word belongs to Caleb Scharf. On a finite world, a cosmic perspective isn't a luxury, it's a necessity. So next time you go back to all of your devices where you have profiles about yourself, make the first thing that you say about yourself be that you're an earthling, and then try and act like it. So thank you for spending all this time with me.
Jill, can you hear me? Jill? Jill, can you hear me?
Yes, I can.
Okay, perfect. Now we're heading to the Q&A session. So I have a couple of questions. The first one is, human techniques for detecting signals from extraterrestrial civilizations are likely to be limited to cover our galaxy. But is there a special habitable zone in which those long-awaited signals can be found?
Well, some people postulate that the galactic center would be too hostile, too much radiation for life, in particular intelligent life, to exist, and that the far reaches of the galaxy don't have enough energy sources. So there's sort of a galactic habitable zone in the middle. We, of course, happen to be in the middle of that. So perhaps there is a ring of habitability in the galaxy.
Okay, thank you. So the second question is, you were an inspiration for the novel Contact by Carl Sagan. Okay, hold on. Sorry. Okay, in the film, the protagonist manages to travel to another world. If this were real now, what would your message be for that extraterrestrial civilization?
Well, my message would be a question to them. And if you've seen the film Contact, you know what that question is. It's, how did you make it through? How did you survive your technological adolescence, that phase that we're in now, where we have many challenges, in part wrought by our use of technology, and we have technologies that in fact could destroy us at the same time. So how do you get through that bottleneck to become an old and stable civilization?
Okay, thank you. So the third question is, what are no, sorry. You are a scientist who inspires and motivates because of your excellent work and dedication. Could you share a message for girls and women of Colombia to inspire them to dedicate themselves to science?
Yeah. I can't tell you how enjoyable a career as a scientist is, because you are trying to answer your own questions. You're not being told by someone, go do this job, find this answer. They're questions that you've been able to pose, that you're passionate about. And it's like being a detective or putting together a jigsaw puzzle. It's really enjoyable. And so I don't know what your questions might be, but the advice would be learn a skill. Learn how to do something that you enjoy, and learn how to do it very well, better than anybody else. And then use that skill to go answer problems that you find inspiring or enjoyable.
Okay, thank you. Those are some beautiful words. So now the last question is, what opportunities are there for students to work or pass at SETI?
There are data that are available through the SETI Berkeley Breakthrough Listen project, that if you have good computing skills or like signal processing, you can take a look at those data and try and come up with new ways of analyzing it. You can you can use educational materials from the SETI Institute website, seti.org, to do informal education programs with young people. In our country, we have the Girl Scouts and the Boy Scouts, and I'm sure that there's something equivalent in Colombia. But you can take the tools that we've provided on the website and go try and inspire a generation behind you. So young people, and get them interested in STEM education and STEM careers, because kids really have always liked ghosts and creepy crawly things and ET. So you can help educate them and get them comfortable with various physics and chemistry and biology concepts, simply because they really like the idea of looking for ET.
Okay, Jill, those are the questions. We are very, very happy for having you to making part of this Congress, and we send you loves and hugs from Barranquilla, from Universidad del Atlántico, and we invite you to come to Colombia in the future, obviously after the pandemic outbreak ends.
Yeah, we're all looking forward to that future. Thank you. Thank you for having me.
Thank you very much. Have a great evening.
Bye-bye.